Welcome to this lecture on path tracing. This is part 1 of 2, and here the goal is to arrive at a simple path tracer, and then in part 2 we will look into importance sampling strategies to get a reasonably efficient path tracer. So our goal in path tracing is of course to do rendering, and we want to render images with full global illumination. So we want to handle all sorts of light transport phenomena. You can see some examples in this photograph here. For example, we have direct illumination. The sun is coming in through the window and illuminating this scene, but then light scatters throughout this scene. So for example, this green book is reflecting light onto the window frame here, and then this light illuminates it, but sometimes it's also shadowed. So like any other light, indirect light can be shadowed, and we get this indirect shadow here. We can have things like subsurface scattering, and when we have light being reflected onto other surfaces by specular surfaces, then we get caustics, such as these bright little stripes here. These are caustics. So we have many different phenomena that you can observe in the real world. And if you're doing rendering using rasterization, then you'll find it very difficult to reproduce all of these accurately. Now, path tracing is essentially a single algorithm that can handle all of these to some extent. For some of them, it will be very inefficient, but there are good ways to make path tracing efficient, such that it can handle most of the relevant light transport phenomena very efficiently. And that's what we want to learn about. So, in principle, the goal here is to simulate light transport. Here we have some virtual scene with a virtual camera positioned here. And then what happens is that light enters this scene, for example, from the sky, and hits some surface point here. And then at this surface point, the light gets reflected into all directions, for example, into this direction, and then it hits the point over here. And this keeps going on, the light scatters around, and eventually some portion of the light will hit the camera. So this kind of light transport is what we have to simulate with our algorithms to get realistic images. In doing so, a core primitive that we need is ray tracing. I'll explain that a bit more in a second, but for now I want to explain why this has gotten more interesting recently. In 2018, NVIDIA introduced GPUs with dedicated hardware for ray tracing, and this has simply made it quite a bit faster. So on a 2080 Ti, for example, you could trace 10 billion rays per second under certain conditions. But so this is a fairly high throughput, and of course it has gotten even faster since then. And all the other hardware vendors have also added ray tracing hardware to their GPUs now. So you have it on all the NVIDIA RTX GPUs, in AMD GPUs, which are from RDNA 2 or newer, on the major consoles, PlayStation 5 and Xbox Series X or S. You have it in Intel Arc GPUs. And recently Apple announced that they have ray tracing hardware in their M3 and A17 Pro chips, and of course M4 also has it. So it's relatively widely available now. However, it should be noted that the current implementation in AMD GPUs and thus in the consoles is a bit slower than in the other hardware listed here. In terms of API support, you can use this hardware-accelerated ray tracing if you're using Vulkan, Direct3D12 or Metal. And there are also GPU compute APIs for it, namely NVIDIA Optics, AMD Radeon Rays, and Intel Embry. However, if you're using older APIs such as OpenGL, Direct3D11 or WebGL, there this is not available. So if you want to use it, you have to transition to one of these newer APIs. Now, what is ray tracing good for in the first place? Our goal in ray tracing is that we are considering a ray, and this ray is characterized by a starting position O and a ray direction vector omega. And then the question that we ask is basically, if we are looking from point O into direction omega, what do we see? Or in other words, what is the first point in our scene, on scene surfaces, that is intersected by this ray? And the scene surfaces are modeled by triangles, so really we're looking for the first intersected triangle. Now, with ray tracing APIs, you don't really have to think about the ray tracing itself so much, because that's what the API and the hardware is good for. So what you have to do is you have to provide all the triangles in your scene to the API. Namely, you have to build an acceleration structure for all of this geometry. And this will help the ray tracing hardware to perform ray tracing efficiently. And then in a shader, this can be a fragment shader or compute shader, or you can use some of the new shader types introduced for ray tracing, such as ray generation shaders. So basically this is available in all types of shaders. In the shader, you can pass a specification of a ray in terms of ray origin and ray direction, and a handle for an acceleration structure to a trace ray function. And then once that terminates, you can retrieve information about the hit triangle, if there was a hit triangle, or if there was no hit triangle, you can just get the information that nothing was hit. Let me briefly explain what these acceleration structures are and what they do. The by far most common choice for acceleration structures these days are bounding volume hierarchies. And the idea here is that when we put an axis-aligned bounding box around our scene geometry, then in many cases we can terminate our ray tracing early. So if this ray were not intersecting this bounding box at all, then we would also know that it would not intersect any of the triangles inside of this box. And because of that, we could directly terminate the ray tracing procedure and just report that there is no intersection. However, of course, in this case, this is not the case. So this ray clearly intersects this blue box here. But what you do in a bounding volume hierarchy is that you repeat this hierarchically. So you put boxes into boxes. For example, here we now have two boxes, one for the bunny and one for the dragon. And now indeed this ray does not intersect the box for the dragon, so we can directly ignore all of the triangles associated with the dragon. And we keep doing this in a hierarchical fashion, defining smaller and smaller boxes, which are organized in a binary tree. And then if we do it at this fine level here, then the ray tracing can be quite efficient. So it will ignore all these boxes over here, and it will only test the triangles in these two boxes. And for this one, this is actually wasteful, because here we are performing intersection tests, but there is no intersection with the triangle. But then here in the second box, we find the intersection that we were after, and the ray tracing has finished without too much computational effort. Once we have found an intersection with a triangle, we of course want to know a bit more about this intersection. So the ray tracing API can provide us with additional information. Namely, it can tell us what is the index of this triangle, and it gives us so-called barycentric coordinates of the intersection point. That means when we have the three vertex positions of this triangle, then we can use these three barycentric coordinates to construct a linear combination of these position vectors. And out of this, we will then get exactly the intersection point between the ray and the triangle. Now, the nice thing about these pericentric coordinates is that we can not only use them to determine the position that we hit, but we can also use them to interpolate other vertex attributes across our triangle. For example, if we have the 3 normal vectors at the vertices, then we can interpolate those. And of course, after interpolating, we should normalize this normal vector. And in this manner, we get the interpolated normal vector at position x, where we hit the triangle. We can also do this for texture coordinates, and thus we get the interpolated texture coordinate at the hit point. And then once we have that, we can use this interpolated texture coordinate to sample the textures for the material of this triangle. And then, for example, we know the material color and things like roughness and whatever we need to describe the reflectance at this point. So all the BRDF parameters will be available to us then. And of course, it may also be that the triangle has emission, so that it emits light into the scene. And this is also a quantity that we can get then, usually from a texture. The other case that we can encounter when we trace a ray is that the ray simply misses all of the triangles in our scene. And in this case, we don't really need any shading data because there is no surface to shade. However, we may still have emission from the background. So in this case, we only compute an emitted radiance for this ray direction. This can, for example, be a constant sky color, which is very easy to do, or we can sample a background texture. This can be an HDR image, and a great resource for such images is this web page. So if you ever need one, you should check that out. Okay, so now we have something that we can do with ray tracing, namely we can compute shading data, and you can see this in action here. This is the renderer that I wrote in preparation for this lecture. And what I'm doing here right now is kind of uninteresting, namely I'm just displaying the emitted radiance. So you can see the sky, you can see the lamps that are in this scene, but everything else is pitch black, which makes it kind of boring. We don't have any shading yet. So what should we do with ray tracing then? If you look at what game developers have been doing with it in recent years, you find that a lot of it is that they embrace familiar effects. So glossy reflections, soft shadows, ambient occlusion, these are things that are commonly done with ray tracing now. This is perhaps best exemplified by this tech demo here. This is very futuristic. It's in the distant future. You can tell because everything is chrome in the future. But in my opinion, this is maybe in slightly poor taste. So remember, what we are going for is full global illumination, and we want to use path tracing for that. We want all these wonderful light transport phenomena that you can see here. So here is the full path tracer that I wrote in preparation for this lecture. And you can see this is running here right now in real time on a little notebook GPU. And whenever I move the camera, it's just tracing one path per pixel. So this is why it looks a bit noisy. When the camera is still, it starts to accumulate and the results get less noisy. And I would argue that this actually looks kind of nice. And in this scene, you can see, for example, some soft shadows here, which are always difficult to do with rasterization. You can see reflections. You can see global illumination. The global illumination is particularly easy to see when you go somewhere inside. So this room here is not modeled in much detail, but you can see how the light that's coming in from the outside is kind of scattering around in this room, which is nice to look at. And this is the global illumination that we want, and our path tracer can handle this. And of course, you would need a bit more to make this production ready, but in principle, this is useful technology, and throughout these 2 lectures I will tell you about all the technology that went into this path tracer. So now that I have your attention, let me dive into the foundations of path tracing, specifically into the rendering equation. The rendering equation is the foundation of rendering. Basically, if we can solve the rendering equation, we can render images, and that's what we want. So you can see it in full here, and I will take you through it step by step. The goal of the rendering equation is to compute the outgoing radiance at a point x into a direction omega o. So what that means is we are looking at a point x on a surface from a direction omega o, and then the question that we are asking is, what is the color that we see here? This is called outgoing radiance in technical terms. And then the first thing that contributes to this is the emitted radiance. So it may be that this surface point x is on a light source itself, and in this case it will be emitting light, and then we have to account for the light that is emitted into direction omega o. But for most surface points this will simply be 0. And then we have to account for reflected light. That is what this big integral here is for, and this is by far the most complicated part about the rendering equation. So let me start by explaining what kind of integral this is. Reflected light can be coming in from any direction above the point. So we have this hemisphere here, and we have to account for all of these direction vectors. So we are considering directions, which we describe by normalized vectors, and we are interested in all the direction vectors where the dot product with the surface normal vector is non-negative. So basically all of the direction vectors above the surface make up this hemisphere omega x. And we are computing an integral over all of these direction vectors, and then we have 3 vectors inside of this integral. And here's what these 3 vectors look like. In these images down here, we are looking at our scene from a single surface point x. It's somewhere on the street in the scene that I've shown you before. And we are looking here at all direction vectors in the hemisphere at once. That's why this image looks so strangely warped. This is using spherical coordinates, which I will explain in a minute. And so the first factor that we have here in the rendering equation is incoming radiance. So what this tells us is we are at point x and we are looking into a direction omega I, and the question simply is, what color do we see? So that is what this first factor encompasses. This tells us how strong the incoming light is. And then the next factor here is the BRDF, and the purpose of the BRDF is to describe how our surface point reflects light. So we may have a diffuse material where the BRDF is more or less constant, but what you see here is a glossy specular BRDF, and that means the light that's coming in from a certain cone of directions contributes to our reflected light much more strongly than light coming in from other directions, because our surface is like a rough mirror. So if you're somewhere close to the main mirror direction, then you get a strong contribution, and elsewhere the contribution will be much weaker. And then finally we have a geometry term here, And this is simply a dot product between the surface normal vector and the incoming light direction. So this is big when we are somewhere up here, and then down here it's small, it goes down to 0. And the reason why we need this geometry term is that when you have light coming in at a grazing angle, then the same amount of light is distributed over a larger area. So effectively, the surface is not illuminated as brightly. And that's exactly what this geometry term accounts for. Now, our goal is to solve the rendering equation. And in doing so, we encounter two major challenges, two things that make this quite hard. The first one is that we need to know the incoming radiance. But how do we compute this? Basically, this is a rendered image of the scene, just with a slightly strange camera. And we started out wanting to render an image, and now basically we have to do the same thing to render an image. So we have sort of recursion here. We have to know how to do rendering to know how to do rendering. And this is one problem that we will have to address. And then the other problem that we encounter here is that we have to compute an integral over a hemisphere. And this integral is a two-dimensional integral because the hemisphere is a two-dimensional object. And it's not so clear how we should go about computing this. It's not just the integral of the function x squared where you can just write down the solution. It's quite a bit more complicated because the integrand that we have here is complicated, and also we have to figure out how do we even integrate over a hemisphere, which is basically a two-dimensional subset of three-dimensional space, because direction vectors only have 2 degrees of freedom, but they are vectors with 3 entries. So I will talk about how we deal with the incoming radiance here a bit later, but for now let's think about how we can define and how we can compute such an integral. To do this, we need spherical coordinates. Spherical coordinates describe normalized direction vectors, so points on the sphere, using two angles. The first one is called the inclination, theta, and the second one is called azimuth, phi. And then to get from these two angles to a direction vector, we are using these formulas here. The z-coordinate is simply the cosine of theta. And then for the x and y coordinates, we are using cosine and sine of phi and multiplying that by sine of theta. Now, it's relatively easy to verify that this actually gives us normalized direction vectors, because if we take the sum of squared entries of this vector, then for x and y, we get this. And now here we have cosine squared plus sine squared, so this works out to be exactly 1. And then what remains is sine squared plus cosine squared, this time of theta, but this is also just 1 again. So we do get a normalized direction vector here, which is then a point on the sphere. And if we keep theta fixed, then we always get the same z-coordinate. So basically, if we keep theta fixed, we get these blue circles here, or one of these blue circles. And with phi, we are getting these lines, if we keep that fixed. So in particular, if we keep theta in the interval between 0 and pi over 2, then we get a hemisphere where all the z-coordinates are non-negative. So if we have theta 0, then we are up here at the North Pole, and at theta equals pi over 2, we are down here at the equator. Okay, so now we have a way to describe points on the sphere with just two angles. And now we want to use this to compute integrals. But in doing so, we have to be a bit careful, because spherical coordinates are not area preserving. The maybe most intuitive way to see this is to look at a map of the world, as shown here. This is Earth parameterized using spherical coordinates. And then what you can see is that in this image, Antarctica looks really big, and Africa compared to that looks quite small. But of course in the real world, if you put these two continents next to each other, Antarctica is quite small and Africa is quite a bit bigger. So what happens here is that the South Pole is stretched out by this parametrization into one long line. It should just be a single point, but it gets stretched out, so this is infinitely stretched and thus much bigger than it should be. And points close to the South Pole similarly get expanded. So these areas look larger than they really are. And when we want to compute integrals, we have to compensate for that. And I won't derive this here, but the correct way to do it is to use a correction factor of sine of theta. So then the way in which we define an integral over the hemisphere omega of a function f is that we use a nested integral over theta and phi. And in here we are integrating over the function f evaluated at the direction vector that corresponds to these angles. And then we multiply this by sine of theta, so that if theta is close to one of the poles, we have a smaller factor here, and thus we compensate for this area distortion. And in these integrals, phi goes from minus pi to pi, and here theta only goes from 0 to pi over 2, because we only want to integrate over the hemisphere, not over the entire sphere. And with that, we have a useful definition of integrals over a hemisphere. Now, if you happen to be confused by all these Greek letters that I'm using here, I thought it might be nice to have this little overview where all the letters that I'm using in this lecture are given as lowercase and uppercase versions with their names. You should learn this by heart if you want to understand the literature on path tracing, because it comes up frequently. Okay, so now we have a definition of the integrals over the hemisphere that we're dealing with, but we still need an efficient way to actually compute these integrals. And for that, we will be using Monte Carlo integration. I will start explaining this using a 1D example, namely this one-dimensional function that you can see here. Our goal is to compute the integral over this function, so essentially the area below this graph. And the way in which we do this in Monte Carlo integration is quite simple actually. What we do is we take a random number u0, which is distributed uniformly at random in the interval from 0 to 1. So in this case, we ended up with this particular value here of u0. And then we just evaluate the function f at u0. And then that's our estimate for the integral. Of course, this is not going to be exact. This is just an estimate of the integral. But it's an estimate that has a few nice properties. Specifically, what we can do is we can just repeat this. We can do it more frequently. And that means we are taking more random points in this interval from 0 to 1 now. And then we take the average value of all the values of f at these different points. And then this is going to be our estimate for the integral. And now the nice thing is that if we just keep doing this for long enough, if we take the number of sample points to infinity, then this is actually guaranteed to converge to the exact result. And because of that, we call this Monte Carlo estimate an unbiased estimate of the integral. Because in expectation, this gives us the correct result. If we just keep averaging different random results, then we will get exactly the correct result. Now, this was for a one-dimensional integral, but the integral we care about is two-dimensional. We want to integrate over the hemisphere, or later we will actually have a higher dimensional integral. So let's look at how to integrate over a function defined on this k-dimensional unit hypercube. So this is just a fancy way to say that we have a vector with k entries. All of them are between 0 and 1. And our function is defined for such vectors. Then if we want to estimate the integral over this function, over its entire domain, we take n uniform random samples in this cube. So we just take k uniform random numbers from 0 to 1 and do that n times to get these vectors here. And then we evaluate the function f at each of these random points, and we take the average of the results, exactly as in the 1D case. And with that, we have an unbiased Monte Carlo estimate for this k-dimensional integral, and we can even say something about how this converges. There is the so-called central limit theorem in stochastics. This tells us that the error of this estimate will be proportional to 1 over square root of n. So what this means is when we increase n by a factor of 4, then the error will be half as big afterwards. So this is plotted down here. The line here is the theoretical convergence rate. Of course, in practice, you have random results, so you will get some fluctuation around this, but the fluctuation also becomes smaller, so this converges at a very predictable rate. Let's compare that to what we would get if we were just sampling a k-dimensional grid. Then basically you run into the curse of dimensionality. And because of that, the error that you get when you estimate an integral based on samples at these grid cells, the error that you get will be proportional to n to the power of minus 1 over k. So if we set k equals to 2, this is exactly what we had here with the square root, but for k 3 or greater, it's actually much worse. It's converging much more slowly. And in path tracing, we essentially care about an infinite dimensional integral because we have this recursion in the rendering equation. I'll explain that a bit more in a few minutes. But because of that, Monte Carlo integration is very compelling for rendering. Because independently of how high dimensional our domain is, we always get this convergence rate, which is fairly good. So now we have Monte Carlo integration and we know how to define integrals over a hemisphere. Now let us put this together. What we do is we sample a two-dimensional point u in this square here uniformly. And then we turn this into spherical coordinates. So we compute theta by simply taking the y-coordinate of this point and multiplying that by pi over 2. And we compute phi by multiplying the x-coordinate by 2 pi and then subtracting pi so that we end up in this interval here. And then with that we have a parametrization of the hemisphere in terms of these random numbers here, which looks like this. And now we can take a function defined on the hemisphere, f, and interpret this as a function defined on the unit square. So we want to compute this integral here, and previously we defined this in terms of spherical coordinates using this formula here with this sine of theta correction factor. And now we express theta and phi in terms of these random numbers as done here. So then what we end up with is this integral over the unit square. But of course we have changed our domain of integration here. We have squeezed it together a bit. So we need correction factors here to account for that. If you want to derive this properly, you can do it using integration by substitution. But since it's just scaling, it's quite obvious what should happen. Previously, the length of this interval was pi over 2. So we have this as a factor here. And same for this interval where the length was 2 pi. And then, of course, 2 pi times pi over 2 can be simplified a bit. It's simply pi squared. So this is now an integral over the unit square that we want to solve. And then, of course, everything we talked about with k-dimensional Monte Carlo integration is applicable here. So what we do is we just take this random vector u in the unit square. We evaluate the function for that. We multiply by the sine correction factor and pi squared. And that's it. That's our unbiased Monte Carlo estimate for the integral over the hemisphere. Of course, this is only for the hemisphere with positive z coordinates. If we want it for an arbitrary hemisphere centered on some surface normal vector at point x, then we have to rotate our coordinate system to map this hemisphere onto this standard hemisphere. And to construct such a rotation matrix, you can use code that is available in this paper linked down here. Now, to actually use Monte Carlo integration, we need one more ingredient, namely we need random numbers. If you're using C++ or C or something like this, you have access to a random number generator in the standard library. But on GPUs, we don't have that, so we have to come up with something ourselves. And what you see here is a pseudo-random number generator that I like because it's relatively good and relatively inexpensive. It's called PCG2D. You can read more about it in this paper linked down here. And the way this works is that we have to give it a seed. So these are just some integers that will be different every time we invoke this function. And then out of this, we get 2 random numbers distributed uniformly in the unit square. So we get 2 random numbers from 0 to 1. And to compute the seed, we can, for example, take the index of our pixel with its x and y coordinates, and then we can add the frame index to that, offset a little bit, so that we really get different random numbers each frame and for each pixel. And thankfully, this implementation here is using an in-out parameter, so this seed also gets updated every time we use this function, which means that we can then use this updated seed again to get another set of random numbers. Okay, so now we have figured out how to compute integrals over the hemisphere. Now we want to use this to actually perform path tracing. So we want to solve the rendering equation. And basically what we have to solve now is this recursive aspect of the rendering equation. So let's say we have our camera here at a point x0 in the scene, and it's for one particular pixel looking into direction omega 0. Then we can use ray tracing to figure out what point on a scene surface is intersected by this camera ray here. And let's say it's this point x1. Now we want to know the incoming radiance at point x0, because this is the color that we should be using for the pixel in the image. And a nice thing about radiance is that it is constant along rays in vacuum. So we are neglecting the possibility of having participating media here, such as fog or clouds or smoke or anything like this. And then we know, it's a physical law, that the outgoing radiance at point x1 into direction minus omega 0 is exactly the incoming radiance at point x0 from direction omega 0. So now by computing the outgoing radiance at this point, we can compute the incoming radiance at this point, which is exactly what we wanted. And to compute outgoing radiance, we can use the rendering equation. Now to do this, we have to solve this integral inside of the rendering equation. And for that, we are now using Monte Carlo integration. So we pick a random direction vector omega 1 in the hemisphere for this point x1. And then we trace another ray, because we again need the incoming radiance here. And for that, we need to know the outgoing radiance at this point x2. So first we have to figure out what this point x2 is using ray tracing. And now at this point, we again want to know the outgoing radiance. But for this, we again have to solve the integral in the rendering equation. And we do this again using Monte Carlo integration, which means we sample another random direction omega 2 and trace another ray to get the outgoing radiance now at this point x3. And for that, we again use a Monte Carlo estimate with one random direction omega 3. And just like that, we have constructed a path. So this path now doesn't hit a triangle, it hits the sky, and that means we get a little bit of illumination here, we get emission from the sky, and then this will make a contribution to the radiance at this point x0. So now we have a contribution to our image. And this is how path tracing constructs paths. That's why it's called path tracing, because you do ray tracing repeatedly to construct a path. And you get a path because every time you want to know the outgoing radiance, you use a Monte Carlo estimate with only one direction. Of course, you could use more directions, but then you would basically get a tree of rays here, and the number of rays that you would have to trace would go up exponentially, which we do not want. So we use path tracing where we only use one random direction. Now, one thing we have to take care of is that, of course, if we were just constructing paths indefinitely, then we have an infinite loop. And of course, we can get lucky that our path just leaves the scene and doesn't hit a triangle, and then we can terminate it. But in a real-time path tracer, it's also a good idea to have a fixed maximal path length. And I want to show you how this affects the results. So here you can see a scene rendered using path length 1. That means you can only see things that are directly emitting light, and everything else is just pitch black. At path length 2, we get direct illumination, so this actually already looks quite nice, but we don't have any indirect illumination yet. We start to get indirect illumination at path length 3, so you can see that everything has gotten a bit brighter. And at path length 4, it gets a bit brighter again, but it's already kind of a small difference in this particular scene. The difference for path length 5 is hardly visible, and path lengths 6, 7, 8, and 9 don't really make any visible difference here. But it's not universally like that, so let me show you another scene that is quite different in this regard. Again, at path length 1, we only see the sky. And then here at path length 2, the direct illumination is mostly the sun illuminating the floor of this living room here. Everything else is still quite dark. And now the light from the sun here starts scattering through the scene at path length 3. So this already looks quite a bit more compelling, and we simply have a lot more light in this scene. We have these very interesting shadows here, indirect shadows. And in this scene, the longer paths really contribute a lot because we have bright walls and a fairly enclosed room. So path length 4 again makes it much brighter, path length 5 still makes it a lot brighter, 6 still, 7 still, 8 still a noticeable difference. At path length 9, well, the difference is maybe not quite as big anymore, but it's still clearly visible. So in general, long paths can be very important, especially in man-made indoor environments. Okay, now with all of this reasoning at hand, we are ready to actually think about how we should implement a path tracer. So what I'll do on this slide is I'll show you complete pseudocode for a very simple path tracer, which I'll then show in action. Our goal here is to compute the incoming radians at a point xk minus 1 from a direction omega k minus 1. So this point and this direction are an input here. And since we want to be able to enforce a particular maximal path length, we also keep track of what the current path length is. And now we start our algorithm. And the first step is that we trace the given ray. So from xk minus 1 into direction omega k minus 1, we trace a ray. And then one possible outcome is that this ray simply missed all of the triangles in the scene. And in this case, we just compute the background emission and return that. So this is just a constant radiance value in the path tracer that I wrote for this lecture, but as explained before, it could also be something that we get from an HDR image for the background, basically an environment map. And then the other case, of course, is that our ray has hit a surface point in our scene. We call this point xk because it's the next vertex of our path. And then we have to compute shading data for this point. Remember, at the beginning of this lecture, I explained how to do this, and then we know normal texture coordinates, BRDF parameters, and we know the emission from this point into direction minus omega k minus 1. Most of the time this is 0, but the point may be on a light source, and then it's not 0. And now, if we have already reached the maximal path length, then there's nothing more to do. We simply return this emitted radiance of this point and we are done. However, if we still want to continue our path, we have to do a bit more work, and this right here is basically the core of path tracing. What we do is we sample a uniform random direction omega k in the hemisphere for the point xk. And the way in which we do this is that we use two uniform random numbers here. We feed them to this spherical coordinates parametrization that we constructed earlier. And then we need a rotation matrix Q that rotates this vector with positive z coordinate onto the correct hemisphere. Remember, I linked a paper on how to construct such a rotation matrix. And now comes the recursive aspect of path tracing, because now we want to know what is the incoming radiance at point xk from direction omega k, and to get a Monte Carlo estimate of that, we simply invoke path trace again recursively. And out of that we get an estimate of this radiance, and then we are almost done, so now we just have to assemble our Monte Carlo estimate. The first term here is simply the emitted radiance, And then we have a Monte Carlo estimate with pi squared and this sign correction factor as derived earlier. And the other things here are simply the three factors in the integrand of the rendering equation: the incoming gradients, the BRDF, and the geometry term. And that's it. This pseudocode is everything we need for a path tracer. Now, if we have a full renderer, we just invoke this function path trace at least once per pixel. So we have a camera array here for which we want to compute the pixel color. And we can invoke path trace once, then we get a fairly noisy Monte Carlo estimate, but we can also do this repeatedly with different random numbers, and then we get a less noisy estimate. And then the L that we get here is the pixel color, of course in a linear color space, so you might want to convert this to sRGB or do tone mapping. Of course, when you compute this sum here with many samples, then it might be nice to show intermediate results, because people don't like to wait to see an image. So just show this every time you have computed one sample per pixel, and that will be a nice progressive preview, and that's called progressive rendering. Of course, when the camera or the scene changes in some way, then you have to reset this accumulation and start over from 0 samples. Okay, and that's it. That's our renderer, that's our simple path tracer, and with that rendering is solved because we now have an unbiased way to solve the rendering equation. Or is it? I mean, maybe it's not quite as simple. So before we celebrate, let's take a look at the results that we are getting here. And well, actually, so this is a path tracer using exactly the methods that I just described, and actually this look quite nice. So when I move the camera, then it's just one sample per pixel, and you can see it's kind of noisy, but it's not so bad. And when it starts to converge, because the camera is still, then it actually converges very quickly. But you may notice that this scene is not exactly the scene that I've shown you before, because here this is daytime, so this is illuminated by the sky and all these street lamps are turned off. And if I change this, if I show you the nighttime version of this scene, you can see that it's actually much more noisy. So when I move the camera here, the image is almost completely useless. It's extremely noisy. It looks darker than it should be because all the energy is in a few seldom bright pixels called fireflies. And if I let it converge a bit, it starts to look okay, but it really doesn't converge very quickly. So this looks much worse than what I've shown you initially. And that probably means that we should put a bit more effort into this path tracer. And that's why we have a second part for this lecture. And in this second part, I will describe all the important sampling strategies that I've used for the path tracer I showed initially. And with that, these images will converge much more quickly. So I hope you have an interest in that and will also join for the second lecture. And with that, I say goodbye or see you at the next lecture.